Our homework was on page 553, due for Friday, but we're going to take a look at it today. Specifically, questions 1 and 2 and 8 and 9. Number 1 says, what is the difference between an electric force and an electric field? Who has an answer for that one for me? The difference between a force and a field. Yep. Okay, good. So the field is a region in which the force could be experienced if there was something there to experience it, right? So what's the big difference there between the force and the field? The region in which the force could be experienced, the force is the force, right? In order to have a field, you just need something to cause it. You just need a producer. In order to have a force, you need to have something to cause it and something to experience it, right? So you need two things, two charges, in order to have an electric force, but you only need one, the producer, to have an electric field. Now, number 2 says, why is it necessary to introduce a field theory? Well, it explains action at a distance. It explains what happens when we talk about gravitational fields, what happens to this board marker due to the Earth, due to the influence of the Earth. It explains that action at a distance. But more importantly than that, it explains that, say, gravity hasn't disappeared just because I take that board marker away. Gravity is still right there. That point that I'm pointing to right now, gravity is still there due to the curvature of space-time, the space-time continuum, whether or not the board marker is there to experience it. So we talk about electric fields. Why is it necessary to introduce electric field theory? Well, because the charge that's causing this thing, that doesn't disappear just because the experiencer disappears. So we have to have a way of describing electricity without having something that experiences the electricity, right? Does that make sense? Number 8 says a small test sphere with a negative charge of 2.5 microcoulombs experiences a force of magnitude 5.1 times 10 negative 2 newtons when it's placed this far from another larger charged sphere. This is a good question. Calculate the magnitude and direction of the electric field at this point. Well, we got two things going on here. We have an experiencer. Okay, this is an experiencer, the thing that feels the field. But then we have this other larger sphere that is a producer that causes a field 0.04 meters away from it. What do we know more about? The experiencer or the producer? Experiencer. Now, we're allowed to use either one of the equations, but we don't know much about the producer, so odds are we're not going to use the producer equation. Let's use the experiencer equation. E is equal to F over Q. And we want to solve for electric field. So the force is 5.10 times 10 to the minus 2 newtons, divided by the charge, which is 2.50 times 10 to the minus 6 coulombs. Not going to forget to convert that to coulombs because I've circled it in red, the microcoulombs in red, right? So let's do the math here. What do we got? 5.1 times 10 to the minus 2 divided by 2.5 times 10 to the minus 6 gives us a value of 20400, which we're going to round to 2.04 times 10 to the 4 newtons per coulomb. Does that make sense? Now we want to find the magnitude and the sign of the charge on the larger charged sphere. Well, we just used the experiencer equation. Got really one more thing I can try here, right, Luke? One more thing. That's the producer equation. We say E is equal to KQ over R squared. Let's find the value of Q here. R squared goes up by multiplying. And then K goes down by dividing. We just found the field strength, 20400 times R squared, 0.04 squared divided by K. I'm not sure what that worked out to be, but you can figure that out, right? Whatever it is, it's going to be in coulombs, and it's going to give you a positive value. Now, that doesn't mean it's a positive charge, just because we got a positive value. Q in the equation is always a positive value. How do you figure out what sign of the charge it is, positive or negative? Who got this? I know some of you did. What type of charge is it? Okay, you don't know right now? I want you to go back and read the stem of the question. So forget about A, just read up here. Okay, just read up here. That's going to give you the clue that you need to determine what the type of charge is. Spencer?
It says the small sphere is negative.
Good. So if it's a negative charge and it's an attractive force, then what kind of charge do we have to have? Right, because the only thing that's attracted to the negative is the positive. So whatever this is, it will be positive, but not because it came out to be mathematically positive here. It's always going to come out to be mathematically positive. It's positive because it's attracted to a negative. You're right. In question A, it does say the magnitude and the direction of the electric field. We found the magnitude, right? The direction, I'm pretty sure you would have gotten this based on the answer you gave me for the second part, but if you didn't, we know that it's a negative. No, wait. No, that's actually harder than I was thinking, actually. We know there's a producer here. We know there's a producer. We know that a negative charge experiences an attractive force, right? That must mean if the negative charge experiences a force towards it, then the field must be, remember, I'm positive the force is with the field. If it's negative, the force is against the field, right? Make sense? So we would say that the field is away from the producer there. That also actually tells us that it's a positive producer, right? Because we established that it's away from it. Does that make sense? I'm positive the force is with the field. So if it's a positive particle, the force is with the field. If it's a negative particle, the force is against the field. The black represents the force here. We were told that it's an attractive force. Therefore, negative particle, the field must be opposite to that or away from the producer. Okay, let's do one more. Question 9A, not crazy bad, although tricky. 9B, crazy bad. Okay. 9A, you could absolutely expect to see that on a test or on an exam. In fact, you will. You will see it on a test and probably an exam as well. 9B is probably a little bit tougher than what you'll see. But we'll go over it because it exercises your mind a bit here. We got a negative charge, 3 millicoulombs. Another one, another negative. We want to find the field strength midway between them. So let's make this 3 times 10 to the minus 3 coulombs. Let's make this one 2 times 10 to the minus 3 coulombs. Let's make the distance 1.20 meters. I want to find the field strength right there, midway between. So let's deal with one field at a time. The field caused by number 1 is this way. How come? How come? How do we know it's to the left there? Spencer? No, actually. The field caused by the first one is toward the negative. It's away from positive. It's toward negative. Now, you can look at this and say, oh, it's away from this other negative. Yeah, but it's not caused by that other negative, so it doesn't matter about that other negative right now. Okay? E1 points towards charge 1. And then we would say E2, ignoring number 1 here, E2 would point which way? The other way. E2 would point this way, towards charge 2. Not away from number 1, just towards number 2. And we can find the values of both of those fields. E1 is 8.99 times 10 to the 9. It's K times Q1, drop the sign of the charge, over r squared, r being 0.60 meters. Well, I don't know what we get when we do that. What is it? 8.99 times 10 to the 9 times 3 times 10 to the minus 3 divided by 0.6 squared. 749. One newtons per coulomb. If you find the value of E2, find it the same way, right? But our charge would be 2 times 10 to the minus 3. For this one, I think we get 499. And then, of course, we just add them up. But when we add them up, Brielle, what do we got to be careful of when we add them up? Yeah, so E1 will be, and E2 will be good. E1 is negative, E2 is positive. When we do that, combine them, we get negative 2.50 times 10 to the, what is that? 2.50 times 10 to the 1, 2, 3, 4, 5, 6, 7. So 2.50 to the left. Oh, and the one you've been waiting for. I know this is like, it's like Friday or Thursday, it was like May, and your favorite TV series is coming to an end for the season, and then there's this cliffhanger, and you can't wait till September to find out what happens. This is the one you've been waiting for. 9B. We're about to find out who lives and who dies here. Okay? We want to find a point here where the field strength is 0. Now, it's going to be somewhere in between, but where? Is it going to be in the middle? Is it going to be closer to number 1, or is it going to be closer to number 2? Closer to number 1? So over here? Right there? Who agrees with that? Nobody. But nobody else is saying anything, so you might be right still, Austin. How many people think it should be over here, closer to number 2? Okay, a few people. Why would you say that, Alex? Why do you think it's closer to number 2? Yep. Yeah, it is closer to number 2. And we know it's closer to number 2 because these fields have to balance in order to give me no net field. And to get the balancing, you know that the bigger charge produces a bigger field. We need a bigger distance to kind of counter that, to make that field smaller again. Austin, does that make sense? Okay. So it is going to be over here somewhere. Where exactly, we don't know. Let's label this distance as r. So that's what we'll find is the value of r. How far away from the first charge is this point where the field strength is 0? Now, we're going to say that the field caused by number 1 is equal to the field caused by number 2. It's actually equal and opposite, but we're going to make the magnitudes of them equal to each other in order to make the net field 0. KQ1 over r squared equals KQ2 over, here's the big leap, the big physics leap. The mathematical leap comes later. What would be our distance here? Cameron? Good. 1.2 minus r. See that, right? This is r, so this has got to be 1.2 minus r, right? 1.2 minus r plus r gives me 1.2. Now, we catch a bit of a break here. The k is the same in both terms. And in fact, the 10 to the minus 3 will appear in each term as well, so we can get rid of that. Q1, therefore, becomes 3 over r squared, and Q2 becomes 2 over 1.2 minus r squared. It's the first thing you think of when you see this now. Okay, cross multiply. Yeah. So we'll say 3 times 1.2 minus r equals 2 r squared, right? Sounds good to me. Okay, the first thing that I think of when I see this is an acronym, a 4-letter acronym. FOIL, anybody else see that? The good news is you don't actually have to do that. It's the first thing that came to my mind when I saw this, but you don't actually have to do it. There's another thing you can do. In fact, you can do whatever you want as long as you do it to both sides, including this. Square root of 3 is 1.7321. So I square root everything in there on the left side. Square root everything on the right side. And this is what we get. Now it's better. Yeah, go ahead. Yep. Yeah, which is the FOIL, right? 1.2 minus r times 1.2 minus r, whatever that works out to be, 1.44, I think, minus 1.2r minus 1.2r plus r squared. Comes ugly, though, right? This is a lot tidier. Let's take the 1.73 over by dividing. So 1.41 divided by 1.7321 equals, right? Seth, I'm going to give you an easy question here. Oh, you got this, Seth. Seth, what's 1 plus 2? Yeah. Do you see that? He didn't even use a calculator for that, guys. 1 plus 2 is equal to 3. Good. Got another one here. Matt. What's 1 apple plus 2 apples? Good. 3 apples. Good. Got smart class here, guys, eh? Okay, I got another one for you here. Let's go, Cameron. What's 1r plus 2r? 3r. Okay, so if 1 plus 2 is 3, and 1 apple plus 2 apples is 3 apples, and 1r plus 2r is 3r, then let's just say 0.816r plus 1r, because I take this over to the other side, equals 1.81647r. Does that make sense? I took 1r over by adding. 1r plus 0.81r is 1.81r. Well, now it's easy, right? R is 1.2 divided by that. .66. So we would say that that point where the field strength is 0 is 0.66 meters to the right of the first charge, the 3 millicoulomb charge. Listen, if you followed along with that and it makes sense to you, you're fine. Okay? If you didn't get it, that's okay. If you did get it, that's great. So much the better. But you're almost certainly not going to have to do something that's this mathematically tricky to do. Okay? But the idea, the physics idea is good here. I'm curious, did anybody actually get that number, 0.66?